Hi, I'm Eric Park, and our presentation is Soap the Moving Teach. So our main objective of the project was to create a water balloon launcher capable of launching up to 25 meters. And what we wanted to do is that we wanted to hit Mr. Day with the water balloon. The water balloons must contain roughly 250 cc of room temperature water, and the launch angle must be at least 45 degrees above horizontal.
Nice, bro.
So I'm Jake, and I'm here to talk about the launcher structure. So the launcher is made of a bunch of wood pieces, and we got two industrial rubber bands to help us launch the water balloons. Now, the bottom, the base of the structure, is basically just a box, and then we decided to screw on two long wooden posts to the sides and attach some the rubber bands to those posts near the top. And then we added a cross beam in between the vertical posts to add some structural support. So we have we actually have the structure in the back of the classroom. If you guys want to take a look at it, I'll probably pull it out for you before this thing even starts. So yeah, go ahead and take a look at it. Check it out. You can mess around with it, play around with it, whatever you want. Yeah.
So the materials we used are 4 wood planks of dimensions 1 by 4 feet,
Potential energy.
2 wood planks of dimensions 1 by 7 feet, 1 wood plank of dimensions 1 by 3 feet, screws to screw the planks together, 2 industrial rubber bands, and a slingshot pocket to hold water balloons.
Good work.
Thank you, Jake. I appreciate it.
Do I say my name? Alright, so... Oh shit. So I'm going to be discussing the energy of the balloon. So the energy of the balloon before the launch, in flight, and just before it hits Mr. Day are the three different I don't know what to say. No, stages of the flight. Alright, we're just gonna go over the energy of the balloon before the launch, in flight, and before it hits Mr. Day, alright? Alright. So before the launch, all you have is elastic energy being converted into kinetic energy. And the math is shown below. In flight, you have kinetic energy and potential energy being converted into kinetic energy and potential energy. And the math is shown below. And just before it hits Mr. Day, or fails to hit Mr. Day, the potential energy and kinetic energy should have changed into kinetic energy, or transitioned into kinetic energy. And that will be shown in the math below. Thank you for listening to the podcast.
Alright, this is the video of the water balloon failing to hit Mr. Day. Alright, these are the graphs.
The Hispanic here? No.
So the 2 questions we are asking in regards to the position and displacement of the water balloon throughout the experiment is how far must the water balloon travel to reach Mr. Day, and where is the water balloon's final position compared with its initial position.
So we used Hooke's law to determine the elasticity constant of our rubber bands, and the formula that represents Hooke's law is force is equal to constant times displacement, and force is represented by F, K is the constant, and X is the displacement. Now we provided a picture here to show you what variables are needed to calculate the elasticity constant of a spring or a rubber band. And so it takes twice as much force to stretch a spring twice as far. So essentially, all these variables remain proportional, and if you double the force, then the distance that is moved is doubled as well. So here are the elasticity calculations. We stretched the rubber band to find out the elasticity constant, and with no tension applied, it covered 1.17 meters, and with 30 newtons of applied force, it covered 1.34 meters, and then with 50 newtons of force, it covered 1.5 meters. Now we use the formula force is equal to negative constant times displacement, and we took the average of the two measurements with 30 newtons and 50 newtons to get an average K value of 163.992.
Hard in the motherfucking paint, nigga.